Let's start chapter number 18, electrical quantities. There are two types of charge, positive charge and negative charge, as this we have already discussed in our previous chapter as well. But some concepts are identical. Inside an atom, we have protons, which is a positive charge, electrons, a negative charge, and neutrons, which has no charge. In a normal atom, number of protons is equals to number of electrons. Charges cancel. Atom is overall neutral, no net charge. Attraction and repulsion. When two charged objects are near each other, they exert a force. Like charges, both positive or both negative repel. Unlike charges, positive and negative attract. Summary: positive and positive repel, negative and negative charge also repel. Positive and negative attracts, and negative and positive also attracts. Charge is measured in coulombs, which is capital C. Demonstrating electrical charges. Charging by friction. When you rub two insulating materials together, they can become charged. Electrons move from one material to another. One object ends up with extra electrons negatively charged, the other loses electrons positively charged. Example: polythene rod plus dry cloth. Electrons move from one cloth to the polythene. Polythene gains electron, becomes negatively charged. Cloth loses electron, becomes positively charged. Acetate rod and dry cloth. Electrons move from acetate to the cloth when you rub it. Then acetate loses electron, becomes positively charged. Cloth gains electron, becomes negatively charged. Here our key idea is only electron moves. Positive charge is left behind when electrons are removed. Let's consider experiment number 1, charging by friction and testing attraction and repulsion. Aim to see how rods of different material behave when charged by rubbing. Basic method: charge a polythene rod by rubbing it with the cloth. Hang the charged polythene rod so it can move freely. Charge rods and charge another rod, polythene, acetate, etc., and bring it near the hanging rod. Observe: if they repel, same type of charge they have, and if they attract, it means they have opposite charge. So conclusions: polythene versus polythene, it will repel as they will be having same charge. Polythene versus acetate, they will attract as they both are having opposite charges. Now improvements: avoid drought, close windows so motion is only due to electric forces. Don't touch the charged ends, you would discharge them. Rub for the same time each trial to compare fairly. Another experiment: detecting charge with a gold leaf electroscope. A gold leaf electroscope, metal plate on top, metal stem and thin gold leaf inside an insulated case. When plate and leaf have the same charge, the leaf rises. Repulsion. Method simplified. Discharge the electroscope first by touching the plate with your finger. Leaf falls. Charge a rod, polythene or acetate, by rubbing it. Bring the charged rod near the metal plate. Leaf rises, charge induced and separated inside the electroscope. Move the rod away. Leaf fall, charge redistribute, electroscope becomes neutral again. Actually touch the plate with the charge rod, charge flow onto the electroscope, leaf stay raised. Touch the plate with your finger, charge flows to earth through you. Electroscope is discharged, leaf falls. Key idea: a charged object near plate causes electrons inside the electroscope to move, induce charge. Touching the plate allow actual charge transfer. Touching with finger allows charge to escape to earth. Let's talk about electric fields now. What is an electric field? It is a region where a charged object experiences a force. Field direction is defined as the direction a positive test charge would move. Electric field lines show direction and strength of the field, always drawn from positive charges towards negative charges. Where lines are closer together, there are stronger fields. Field around a point charge. Positive charge, line radiate outwards. Negative charge, line point inwards. Field around a charge conducting sphere. Same pattern as the point charge. Lines are perpendicular at right angles to the conducting surface. Field between two parallel plates. One plate positive, one negative. Field lines can be straight, parallel, and are equally spaced. This is a uniform electric field. Same strength everywhere between the plates. Investigating conductors and insulators. Definition: conductor, a material that allows charged electrons to flow easily. Example: metals, copper, aluminium, silver, steel. In metals, positive metal ions in a lattice, delocalized free electrons move through, carry current. Insulators, a material that does not allow charge to flow easily. Example: rubber, plastic, glass, dry wood. No free electrons to move through the material. Experiment using a gold leaf electroscope to test conduction. Aim: to distinguish between good conductors and insulators. Method: charge the electroscope so the gold leaf is raised. Touch the plate with different material: metal, glass, wood, plastic, etc. Observe how fast the leaf falls. Interpretation: leaf falls quickly. Material allow charge to flow away. Good conductor. Leaf falls slowly. Poor conductor. Leaf doesn't move. Very good insulator. Expected results: good conductors, metal, graphite, leaf quickly drops. Poor conductors, insulators, plastic, glass, rubber, dry wood, fabric, leaf slowly drops or doesn't move. Let's talk about current. What is current? Current is the rate of flow of electric charge. In metals, current is due to the movement of free electrons. Conventional direction. Current is taken as flowing from positive terminal towards negative terminal of a cell. Electrons usually flow from negative to positive, but we still use conventional. Alright, so electrons actually flow from negative to positive, but we still use conventional currents. Measuring current. Measuring currents, use an ammeter. Ammeter is always connected in series with the component. Analog ammeters, needle and scale, must avoid parallax error. Read from directly in front. Check for zero error before use. Digital ammeters show readings as numbers, can measure very small currents, even in milliampere and microampere. Also check for zero error and possible flickering readings. For current, we have a formula: I equals to Q over T, where I is current measured in ampere, Q is a charge measured in coulomb, and time in second. So we can rearrange the same equation as Q equals to IT, or if we need to calculate T, then Q over I. Meaning 1 ampere is equals to 1 coulomb of charge passing a point every 1 second. Let's talk about direct and alternating current. Direct current DC, a current that always flow in the same direction, produced by cells, batteries. Voltage of a cell is constant and always has fixed positive and negative terminal. Alternating current AC, a current that reverses direction repeatedly. Terminals keep swapping between positive and negative. Mains electricity is AC. In the UK, about 230 volts 50 Hz changes direction 50 times per second. On a graph, current versus time, direct current, straight horizontal line, constant current, Alternative current, smooth sine wave crossing above and below zero. Electromotive force, EMF. Definition: electromotive force of a source is the energy supplied by the source to each coulomb of charge as it moves around the whole circuit. Definitions are important everywhere. Whenever we present you any definition, learn them as it can be tested for the exam. It is basically the voltage of a cell or power supply. Formula: E equals to W over Q. E is electric motive force, unit is V, voltage. W is energy transfer from the source, unit is joules, J, and Q is actually a charge which is measured in coulomb. Potential difference, PD, across a component is the energy transferred from charge to that component per unit charge. The formula is V is equals to W over Q. V is potential difference, W is energy transferred to the component, and Q is the charge. 1 volt is equals to 1 joule per coulomb. Measuring PD, use a voltmeter. Connect it in parallel with the component. Reason: potential difference, the difference between 2 points. Voltmeter must compare 2 points. Voltmeters analog, needle and scale, watch parallax error, check for zero error. If it's digital, more precise, easy to read. Again, check for zero error and display stability. Now let's discuss about resistance. Definition: resistance is the opposition to flow of current. Physical idea: in a metal wire, electrons move and collide with metal ions. This collision resists the flow and transfer energy. Wire warms up. Larger resistance, small current for the same voltage. Formula: Ohm's law. It is equals to R equals to V over I, where R equals to resistance, V is equals to potential difference, I equals to current. So for a fixed voltage, increasing resistance decreases current. For a fixed current, increasing resistance increases potential difference across it. We have a graph for current voltage where you can show the relationship between the current and the voltage. This is the threshold voltage. Ohmic conductors, constant resistance. Example: fixed resistors, metal wire at constant temperature. The current voltage graph is a straight line through the origin. Current is directly proportional to voltage, so resistance is constant. Ohmic resistors and non-ohmic resistors. Ohmic resistors that obey Ohm's law. Any increase in voltage creates a linear increase in the current. Non-ohmic resistors do not obey Ohm's law. Any increase in voltage creates non-linear increase in current. The resistance of the material change based on the current moving through it. What are ohmic and non-ohmic resistors? This is another example of with the shown in the diagram. Non-ohmic conductors, variable resistance. So filament lamp, as current increases, filament gets hot. Hotter filament, ion vibrate more collision resistance increases. The graph is a curve that becomes flatter as voltage increases as shape, shows resistance increasing with current and temperature. Now let's discuss diodes. It allows current only in one direction. Forward bias, current flows easily after a certain voltage. Reverse bias, almost no current, very high resistance. This is an example of a diode. The graph shows no current for negative voltage, sudden rise in current when forward voltage is reached. Another example in the form of diagram. Now let's talk about resistance of a wire. Effect of length and thickness. Longer wire, electrons travel further, more collision, higher resistance. Thicker wire, larger cross-sectional area, more space for electrons, more paths, lower resistance. Mathematical relationships, proportionality. R is directly proportional to L. So resistance is directly proportional to length. Resistance is inversely proportional to cross sectional area. So we have two relationships here. Then let's discuss about electrical energy. Energy transfers in a circuit. As charge flows, it gains energy in power source, cell, battery, main supply. It transfers energy to components, lamps, motors, heaters. Example motors, vacuum cleaners, washing machines, fridge. Electrical energy, kinetic energy, moving parts plus some heat. Heaters, kettles, toasters, radiators. Electrical energy, thermal energy, heating elements surrounding. Okay, energy in electrical circuits formula is E is equals to V times I times T. V E is for energy, V is potential difference, I is for current, and T is for time. Let's talk about electrical power. Power is the rate at which energy is transferred or converted. Our definition has the formula P equals to E over T. Or for electrical components, we can use P equals to VI. So we can write ET equals to VI as well. So P is for power, watts is a symbol, V is potential difference, I is current, ampere. Unit 1 watt equals to 1 joule per second. Energy in kilowatts per hour. For household energy use, we often use power in kilowatts, time in hours, energy in kilowatts per hour. So our formula will turn into this. Conversion 1 kilowatt equals to 3.6 times 10 power 6 joules. To convert kilowatt to joules, we have to multiply by 3.6 times 10 power 10. To convert to joules to kilowatt, we have to divide by 3.6 times 10 power 6. Example, a 2 kilowatt heater used for 3 hours. So you see energy is 2 times 3, 6 kilowatt. If electricity costs say 0.15 pounds per kilowatt, our total cost will be 6 times 0.15, which is 0.90 pounds. This is how electricity bills are calculated using power ratings, time of use, and price per kilowatt per hour. With this, we have finished our chapter. See you in our next chapter.